Thank you so much, Petrix. Thank you so much to the organizers for putting together this lovely conference and giving me an opportunity to talk. So what I'll tell you about is, so we had these two papers with Stefano Antonini, Luca Iliescu, and Pratik Rath, who are all at Berkeley. And my talk will be based on this first part, and then Stefano will continue with the second part. Okay, so before we begin, since Stefano and I are giving these two parts, and we are to blame for some of the unpleasant things that have been discussed and will be discussed at this conference, I would like to start with a disclaimer that no closed universes will be harmed in this talk. Don't worry about it. Although some black holes may be at a bit of risk. And the other thing I realized by talking to some of the people here was many of the younger people in this audience might completely miss the fact that this title is a tribute to this 2000 paper. So that's where the pun comes from, and something I'm very proud of. Okay, so now let's begin. So Ahmed very nicely reminded us yesterday of the central dogma of black holes, which is that black holes basically behave like regular chaotic quantum systems with a number of states that's given by the Bekenstein-Hawking formula. And of course, this is something that we learned by just testing things from a low energy perspective. There have been string theoretic ways in which we saw this, but largely all the progress that we've made in trying to understand the central dogma has been from a bottom-up perspective, where we try to use tools like the gravitational path integral to try to see how it's consistent with this central dogma. So that's sort of the broad goal, where how many aspects of this can we test just using a low energy analysis. And the tool we're going to use is the gravitational path integral, which of course gives us answers to some of these questions, but sometimes it's a coarse-grained answer, and so we need to be careful about how to analyze things. So examples of this, of course, include the famous calculation of the Page curve, where naive semi-classical gravity told us that the entropy keeps increasing forever, but we found new saddles in the gravitational path integral, which turn the Page curve down and give us something consistent with unitarity, and in particular, the central dogma. There's also the spectral form factor, where what gravity is able to reproduce is not precisely this erratic red curve, but what it can reproduce is a coarse-grained version of it, which is just the smooth black curve, right? So just to contrast these two situations, in the Page curve case, we could also think about the calculation that the gravitational path integral is doing as coarse-grained, but it doesn't really matter. Like, since it's a self-averaging thing, it doesn't really matter that we're computing it for a single theory or for an average. Whereas in the case of the spectral form factor at late times, it really does matter. So what I'd like to emphasize from this is essentially, if we can phrase things in a self-averaging manner, then we can answer them using the gravitational path integral and be sure that this is telling us something about a particular theory of quantum gravity instead of some average. Okay, so the particular question that we'll be after in this talk is the third law of thermodynamics, right? And in particular, it says that in the absence of any symmetries, is there a unique isolated ground state for these black holes? Or equivalently, we could phrase the question as saying, does the entropy go to zero as we take beta to infinity or take the temperature to zero? So, of course, from the central dogma, we would expect that this is just some generic quantum system. In the absence of any other symmetries, we expect that there's a unique ground state. And so the expected answer from a top-down perspective should be yes. But this is really non-trivial to see from a low-energy description using the gravitational path integral, because this question, at least in the settings we'll look at, really probes the discreteness of the microstate. So just like the spectral form factor, it's something that's very sensitive to the discreteness of these microstates. And that's something which is non-trivial to see from a low-energy perspective. So in our analysis, we'll see that even though we expect the answer to be yes, it's going to be hard to see that from the low-energy perspective. Okay, so the setting in which I'll work is JT gravity, which was also nicely reviewed yesterday by Ahmed, which is, of course, a solvable 2D theory of gravity. And it involves two fields, the metric and the dilaton. The action is as follows. There's a topological term, and then there's the action which remains here. When you integrate out the dilaton, you're just left with integrating over metrics, which satisfy r equals -2. So the gravitational path integral will just sum over all such hyperbolic geometries. This sum is organized in this genus expansion. So suppose we compute the partition function. It has an expansion in genus where each of these terms is weighted by powers of e to the s naught, suppressed by their genus. And so for example, the leading term is just the disk with a boundary of size beta. On the disk, we just do an integral dictated by this action, which is just the Schwarzian action. And that's a one-loop exact calculation, which can be done precisely. And then we look at higher genus terms. Again, in higher genus terms, we can decompose the calculation into what's called the trumpet and everything else. Again, that can be done exactly. And this was all done by, a lot of it was done by Saad Shankar Stanford. And we understand all of this pretty well at this point. Okay. So now JT gravity in particular describes black holes, but it has a continuous spectrum. The spectrum looks like the following. The density of states at leading order is just e to the s naught times this sinh of 2 pi square root e, which near the edge of the spectrum looks like a square root. So it's the square root edge near the edge of the spectrum, which is continuous in particular. So you might wonder, like, this is already a continuous spectrum. Why doesn't this kill the idea that I was talking about? And of course, we now understand that that's because JT gravity, the gravitational path integral of JT gravity, really computes an ensemble average over random Hamiltonians. So the real question that we're after is not whether this spectrum is continuous or discrete, but it's really that we want to look at every individual member of this ensemble and ask whether it has a discrete, isolated, unique ground state. Or equivalently, does every individual member satisfy the fact that the entropy goes to 0 as beta goes to infinity, or the temperature goes to 0? Okay. Okay. And in particular, we like to see this. This is obviously true from the random matrix theory perspective. In the random matrix, there's just discrete spectra with and typically the ground state is just unique because of eigenvalue repulsion. So it's sort of obvious from the boundary side, but how do we see this from the bulk, and in particular from the path integral? Okay, so in order to talk about this, I'll first have to talk about different kinds of entropies we can talk about when we have an average over theories. So instead of talking about the entropy, it'll be convenient to talk about the second Renyi entropy. That'll be something that's more easy to compute, which is given by the following, is just minus log of trace rho squared divided by trace of rho whole squared. And now we need to decide where to put the averages. So we need to decide which average to compute for this. The first option, which is actually the simplest thing we can try to do, is what's called the annealed entropy. So the annealed entropy is where we put the angles, which is the ensemble average, as inside as possible. So we try to compute the average of the numerator and denominator separately, and also compute the average here before we take the square. This is the standard way in which entropies are computed in holography. In particular, most derivations of the RT formula essentially do this. This is a one boundary partition function. This is another one boundary partition function. And we just compute the difference in actions and try to understand, and then analytically continuing that gives us the RT formula. So while this is the simplest thing to compute, it's not necessarily positive or even physically relevant. So in situations where it's different, in situations where this quantity is not self-averaging, we don't necessarily assign it any physical meaning. And one way to see that it's not necessarily positive is that when we're computing this quantity, it's like computing the entropy of a state which is only normalized on average. So suppose we compute the average norm of the states in this ensemble, and then just take any individual member of it, compute the entropy of that by normalizing just by the average norm. There will exist instances where this is not sufficient to give you a density matrix that's supported in 0 to 1. And so it can have negative entropy when you try to compute this. So on the other hand, the better option, of course, is to try to do the averages at the end. We want to do it as outside as possible. That's what's called the quenched entropy. So here we just put the average right outside the log. But that makes it challenging. So this is difficult to compute because in particular, it requires this no replica trick, which is to compute the expectation value of log of something. We need to do this trick where we compute the expectation value of z to the m. So we consider m boundary versions of this, and then analytically continue in m to 0. When you do this, you find the log. But this analytic continuation is actually quite subtle, and as I'll emphasize later in the talk, this analytic continuation to m equals 0 will actually not commute with the low temperature limit. So this thing is really subtle, and that's why this is difficult to compute. But on the other hand, it is positive, just because it's computing the average entropy in this ensemble, and each of them is positive, and we're computing a positive average over positive quantities. So this is positive. And of course, it's also physically relevant because it's really telling you what the average true thermal entropy of this ensemble is. Okay, so now we're sort of stuck in between them, and what we thought was useful was to invent a sort of intermediate quantity. So this is what we defined to be the semi-quenched entropy, which is somewhere in between. Here we take the averages in the following way. We average over the numerator and denominator separately, but we include the square inside the average. So it's quite close to the annealed entropy, except that the denominator now is a two-boundary partition function. And in particular, we know that when we ensemble average over these things, they will differ by connected geometries which connect these two boundaries. However, once you have that, you can show that this quantity is actually positive. If you have a discrete spectrum, this quantity has to be positive. It's not so clear whether it's physically relevant. We don't have a operational meaning so far for this quantity. But the reason it was useful for us was because if you can show that this quantity is positive and it just goes to 0 as you take the low temperature limit, then this is enough to imply that that almost all theories in your ensemble have an isolated ground state. The way to see this is roughly if you had some member of the ensemble, or at least a non-measure zero set of the ensemble, which had a continuous spectrum near the edge of the spectrum, then this quantity actually goes negative. And when you're taking the low temperature limit, all the discrete ones essentially go to 0 and they don't matter, whereas the ones which are continuous dominate the answer and become negative. So proving that this thing is positive and goes to 0 is sufficient to imply the third law of thermodynamics. And in particular, it also tells us that the quenched entropy also stays positive and goes to 0 as we take this low temperature limit. Okay. So let's start with the calculations. Let's first do a naive version of this calculation, which is just the disk approximation that is usually used to compute the thermal entropy. So the partition function just on the disk has an e to the s naught from the topological factor and a 1 over beta to the 3/2 coming from the Schwarzian fluctuations at large beta. If you take this and compute the entropy, what you find is that the entropy is given by S naught, which is just the ground state entropy, minus 3/2 log beta. And the interesting feature here is that this is usually a small correction at high temperatures, but at low temperatures, when beta is large, this can become important. And in particular, a naive extrapolation of beta to order e to the 2s naught over 3 naively tells us that this quantity goes negative. So at the disk level, this is the answer we find, and we want to make sense of this. This, to my mind, was first pointed out by these authors. So the intuitive explanation for why this is happening is what we're doing is really computing an annealed entropy, and the annealed entropy does go negative at these really large beta because there's a large suppression, there's a large Boltzmann suppression coming from this beta, which basically zooms us very, very close to the ground state. And if you have a continuous spectrum and you're zooming in very, very close to the ground state, effectively the number of states that's contributing to this entropy is less than 1. Since it's continuous, it doesn't need to be at least 1. So the dimension, the effective dimension here is less than 1, and log of that dimension is then negative. So that's sort of intuitively why the annealed entropy is going negative when we take really large beta. Okay, but this calculation, I mean, taking beta to be exponentially large in S0 is really outside the regime of validity of the original genus expansion. It's because that genus expansion assumed that nothing else depended on e to the S0. We just had an expansion in e to the S0 with other quantities independent of e to the S0. So we have to do something better, and that's where this Airy limit shows up. So instead, we'll work with a double scaling limit where we hold fixed the ratio of beta to e to the 2s0 over 3, and we'll call that alpha, and then take beta and e to the s0 both to infinity. In this double scale limit, the behavior of this theory is actually well understood. On the matrix model side, this thing basically zooms in very close to the square root edge. And it's a universal fact about random matrix theory that these square root edges are controlled by what's called the Airy matrix model. This is something that was studied a lot in the 90s and so on. And so the main difference is when you account for this thing, the spectrum, instead of looking like this yellow curve, which was just the square root edge, has some wiggles which are given by this the Airy density of states. Okay, but moreover, we can also make sense of this on the bulk side. So on the bulk side, we had this expansion in genus, as we had before, which was the disk plus the genus 1 and so on. We can try to work now in a large beta regime where we can expand these partition functions in powers of beta and use properties of the Weil-Peterson volumes to have this double sum where we have a sum over genus, but also sum over these powers of beta with some coefficients. These coefficients can actually be computed. This was basically what was solved by Kontsevich and then computed by others like Okounkov and so on. And here, since we're at large temperature, large beta, we can essentially drop all the higher terms and keep just the L equals 0 term. When you do that, this thing is actually a convergent expansion in genus. And you can resum this genus expansion to get some function which I've called the resummed disk. It's not like it's dominated by just the disk. It includes contributions from all of these genus, but that sum can actually be done explicitly. And just to show you that it can be done, this is what the function looks like. It's pretty simple. It just has this exponential of alpha cubed divided by alpha to the 3/2. Okay, so once you have this, you can still compute the annealed entropy, and as expected from the fact that even the Airy density of states has a continuous spectrum, you find that the annealed entropy still goes negative at sufficiently large alpha, and the physics is pretty similar. Okay, so now it's important for us to look at the semi-quenched entropy, since the annealed entropy went negative. And just to remind you, the semi-quenched entropy in this particular context is given by the ratio of z of 2 beta average divided by z of beta squared average. So z of 2 beta is just given by the disk with boundary of length 2 beta plus the higher genus version and so on. So it's just what we wrote in the previous slide, except evaluated at a boundary length of 2 beta. And z of beta squared has two parts. It has a disconnected part, which is basically just the product of two of these, plus the connected part. And the connected part will play an important role here because that's what distinguishes it from the annealed entropy. So the connected part will involve a cylinder plus higher genus versions of the cylinder and so on. And again, in this limit, this sum can be exactly done. You can resum the contributions from all of these higher genus geometries. And you find some function, which I'll call the resummed cylinder as a function of the boundary lengths. Again, just to show you that this can be explicitly done, here's what it looks like. It's just some exponentials with some error function and so on, with some explicit function that we can work with. An interesting feature here is that we can look at z of beta squared as a function of beta. At high temperatures, we expect that the disk is the dominant contribution, and that's what you see here. So this is as a function of temperature. The sum of the disk and cylinder is this green curve. The disk is this blue curve, and the cylinder contribution is this orange curve. So at high temperatures, we see that it's dominated by the disk, but as we go to lower temperatures, it's actually dominated by the cylinder. So in the regime of our interest, it's actually these cylinder diagrams, which is the connected part, that dominates the answer. Okay. So given that, we can then try to see what the plot for the semi-quenched entropy looks like. And the interesting feature here is that at large beta, the partition function z of 2 beta actually approaches the connected part of z of beta squared. So this is some highly non-trivial fact about JT gravity, because, I mean, it sort of had to be true from the random matrix theory side, because we had this discrete spectrum and we expect the semi-quenched entropy to go to 0. But it's a highly delicate and subtle calculation on the bulk, because the left-hand side involves geometries which are single boundary geometries summing over all the genus with a boundary length of 2 beta. And the right-hand side involves cylinder and higher genus versions of the cylinder. There's no obvious geometric way to see that this had to be the case, but the JT gravity path integral is precisely such that this is satisfied. Since this is such a constraining fact, you might even imagine if you have some sort of putative gravitational path integral, this puts rigorous constraints on it, and you might imagine some sort of wormhole bootstrap where there's some relation between 1 boundary partition functions and 2 boundary partition functions and so on, and it's quite constraining. Anyway, when we take this function that we wrote down in the previous slide and plot it, this is what we find for the semi-quenched entropy. The blue curve here is the annealed entropy, which went negative at sufficiently low temperatures. And the semi-quenched entropy is basically the same as the annealed entropy at high temperatures. But then as we go closer and closer to low temperatures, it deviates and it eventually goes down to 0. So since we've showed that it stays positive and goes to 0, this is sufficient to actually prove that there's an isolated, unique ground state and in almost all members of the ensemble. Okay, so there's a slightly different way of understanding this, which is this idea of understanding it in terms of eigenvalue instantons in the random matrix theory. This was an idea that was proposed by Sergio Hernandez-Cuenca. And the idea is the following. So when we're computing something like this, where we have, say, z of n beta raised to the power of m, in the matrix integral, what we're doing is we have an integral dh with some matrix potential e to the minus nv of h. And we're just inserting a trace of e to the minus n beta h to the power of m in this matrix integral. Right? So now at large beta, we can approximate this trace by essentially just the contribution that's coming from the leading eigenvalue or the lowest eigenvalue. Since beta is really large, the contributions coming from subleading eigenvalues are exponentially small. And so we can approximate this trace by just the leading piece, which is just this lowest one. Once we do that, this is just the exponential of something. So we can just think about this minus mn beta e naught as being added into the potential. So this is just some deformation of the potential, which is just a term that acts only on the lowest eigenstate. So this will now have some new equations of motion, which are deformed from the original equations of motion of the random matrix theory. And essentially, the difference is this force that's acting on the lowest eigenvalue. And in particular, there's an enhancement when E naught becomes more and more negative. And so there's an additional force for the lowest eigenvalue to become smaller. So what it looks like is the following. We had this original solution, which was this yellow curve, which was given by this Airy density of states. But now when we add in this function, there was an exponentially small probability for the lowest eigenvalue to be at these negative values. But now there's a huge enhancement coming from this insertion. And so there's some sort of competition for where the lowest eigenvalue wants to be. And in fact, there's an instanton, which is where this lowest eigenvalue is separated from the continuum. So most of the eigenvalues just stay where they were in the original solution. And the lowest eigenvalue just escapes from from the bulk of the spectrum and goes further negative. So this is what is called the one eigenvalue instanton, where a single eigenvalue has escaped from the continuum. And this is what dominates the answer for z to the m. So the physics of this is basically that as you make beta larger and larger, the answer for z of beta to the m is dominated by members of the ensemble with a large first gap. So it wants the lowest eigenvalue to be as negative as possible, whereas the second one just stays close to the edge. And so the gap between them is growing. Okay. So we can analyze this in a saddle point approximation. There's a saddle for this. We can expand around it. And what you find is that this is a controlled expansion as long as alpha times mn is much bigger than 1. So for the purposes of computing the semi-quenched entropy, what we wanted to compute was z of 2 beta, which is n equals 2 and m equals 1, and z of beta squared, which is n equals 1 and m equals 2. Since m and n here are just some finite numbers, all we need is for alpha to be really large. So when alpha is really large, this eigenvalue instanton analysis works. And what you find is since the potential only depended on the product of mn, these two are basically the same, and so they cancel to leading order, which is what we saw from the JT gravity analysis as well. They are different at subleading orders, and the subleading correction to this ratio comes from a 2 eigenvalue instanton. I won't have time to talk about this, but you can ask me more if you're interested. And that precisely matches with the Airy analysis. So when we take alpha to be order 1 but large, that is consistent with the Airy limit. And so there's an overlapping regime of validity between the Airy calculation and this instanton calculation. And we find that there's an exact match between them, as you might expect. But also, this eigenvalue instanton calculation also works for larger alpha. So if you have alpha scaling with, say, e to the s naught, for beta scaling with e to the s naught. And while this Airy calculation is quite universal, in random matrix theory, there's a universal behavior near the square root edge. The behavior far from the edge is actually quite non-universal, and it depends on the potential. But nevertheless, once you have a potential, you can find out where this instanton is. Okay. Good. So having talked about the semi-quenched entropy, we've proved that the quenched entropy has to stay positive and go to 0 at 0 temperature. But what else can we say about it? Can we actually compute it? And the issue is we can try to use this eigenvalue instanton analysis, but you find that the order of limits actually don't commute. So taking beta to infinity versus taking m to 0 is an issue, because we saw here that the expansion is controlled as long as alpha times m is big. So depending on which one you take to, whether you take alpha to infinity first or m to 0 first, this analysis is valid or invalid. And the order of limits we're actually interested in to compute the semi-quenched entropy is where you take m to 0 first, so that you're computing the quenched entropy at some finite beta, and then take the limit of beta goes to infinity. That's the opposite order of limits that was being used in the saddle point approximation, because we were first taking beta to infinity, doing the saddle point approximation, and then taking m to 0. So this doesn't quite work because the saddle point approximation fails when you try to take this limit. For any m which was away from 0, this was a fine analysis with the eigenvalue instanton, but it breaks down for the quenched entropy. And this is quite analogous to the issue of the order of limits between g going to 0 and n going to 1 for the entanglement entropy. So often in holography, we first do the saddle point approximation at arbitrary n and then analytically continue that answer to obtain the entanglement entropy. But really, for the entanglement entropy, what you truly want to do is first take the n goes to 1 limit, then take g goes to 0. Often this doesn't matter. And in practice, there's only few examples I know where it does matter, which is, for example, where you have fixed area states. If you have some fixed area state and you want to compute the entropy of some other region which crosses it, then the fact that you fix the area sharply induces large fluctuations in other areas. And in those situations, there's a big difference between computing the expectation value of something like e to the minus n minus 1 times the area versus computing the expectation value of the area. This first calculation is actually dominated by smaller areas. You want this exponent to be as small as possible, whereas the expectation value of the area is actually dominated by larger values of the area. So there are some situations when these fluctuations can be large, where this does matter. And so this quenched entropy analysis is basically exactly analogous to that. So Nevertheless, you can try to compute it from the random matrix theory side. So when you take beta to be really large, the important contribution comes from the lowest state and the first excited state. You can drop the contributions coming from everything else. And this was done in particular in this paper by Janssen and Mirbabai. When you do this analysis, you find that the answer only depends on the probability distribution of this first gap. In random matrix theory, this gap basically goes like delta to some power s, which is fixed by the symmetry class of the problem. This is basically eigenvalue repulsion completely fixes this probability distribution. And when you do that, when you use this, you find that the entropy behaves like a power law. So it goes like 1 over the inverse temperature to the power of 1 plus s, where this s is again fixed by the symmetry class. So in particular, it's not an exponential decay, but it's a power law decay. So the physics of the quenched entropy is quite different from the semi-quenched entropy. As you can see here, the dots here are a numerical evaluation of the quenched entropy, and you see that it's much larger. And in particular, if we zoom in close to the zero temperature regime, you see that there's a power law behavior on this log-log scale, whereas the semi-quenched entropy decays exponentially. Okay, so the physics of this is quite different from the semi-quenched entropy, as I emphasized. There it was dominated by atypical members, which are exponentially atypical, but they have a large gap between the first and the ground state and the first excited state. Whereas here, it's more dominated by small gaps. If you have a small gap, the entropy is a little bit larger, and so the things that contribute to the quenched entropy are actually things with small gaps. So the physics changes quite a lot when you try to go from the semi-quenched entropy to the quenched entropy, and that's what makes this a hard problem. This m goes to 0 limit is quite subtle. Okay, so let me just make a few more comments. This was an analysis in pure JT gravity, but we can try to see how it generalizes to other theories. In particular, if you want to add matter, for example. Since this required a full resummation of the path integral, it's quite subtle to do when you have the presence of matter. So instead, what we had done was just some numerical analysis in the SYK model for the quenched entropy. And at least in this, the law is usually that random matrix statistics works well when you're in the bulk of the spectrum, but near the edge, it can be quite different. At least in the SYK model, we find the power law behavior of the quenched entropy is quite similar because of eigenvalue repulsion of a similar form. So for example, in GUE SYK model, you have this quadratic behavior for the gap distribution, which leads to which leads to a power law for the semi-quenched entropy, for the quenched entropy. And here in particular, you see all of these red lines are like contributions to the entropy from individual instances, which are all quite small, whereas the average is basically dominated by some of the larger contributions to the entropy, which have really small gaps. So these are also atypical members, but they have small gaps. Okay. Now, again, as I was saying, the edge of the spectrum is not expected to satisfy random matrix statistics in general. So it would be interesting to quantify deviations from random matrix statistics, even in a model like SYK. And there's been some proposal by Altland and collaborators about this, and this is something I'd like to look into. We can generalize this at least within pure JT gravity to other symmetry classes. We worked with the GUE symmetry class, but if you have other symmetries, these were all worked out by Stanford and Witten, and the analysis should be similar, except the Airy limit may not be as well understood. So that's something that's left for future work. And then we can wonder about what aspects of this apply to higher dimensions. In some sense, higher dimensions are a little bit easier, but also tougher. In higher dimensions, if you have a CFT, the ground state is just the vacuum. And so there's no continuous spectrum near the vacuum. And so it's almost trivially should give you a zero temperature entropy of 0. But if you then project onto some sectors which only involve black hole states, the ground state of the black hole part of the spectrum should have similar features where there's almost a continuous spectrum, and you would need some higher topologies and so on to see that you really have a discrete ground state for that sector. And of course, we don't understand the path integral well enough, so that calculation is much harder. Okay, and finally, I'd like to close with some open questions, which is, can we have a controlled calculation of the quenched entropy? There's been a lot of analysis of this, but because of the issues that I talked about this m goes to 0 limit, it's actually a quite subtle calculation. There were some attempts made in this paper, but I think we don't have a full story about how this could be done. So that's something that's an interesting open question. And can we have some sort of semi-classical description of these bulk geometries? So almost done. We saw that the answer for the semi-quenched entropy came from resumming all of this higher genus contributions. It was not dominated by a single saddle. But in this paper, they tried to argue that that can be thought of as a single saddle of a deformed potential. So that's something that is also interesting. Okay, thank you.
Thanks, Pratik. So I have a question about the argument that semi-quenched entropy going to 0 implies ground state.
Yes.
So as I understood the argument, you said continuous members of the ensemble would have negative semi-quenched entropy, whereas isolated members would have 0.
Yes.
But it seems to me that you haven't ruled out the possibility of having members of the ensemble with degenerate ground states, which would have a positive semi-quenched entropy. You could imagine that those could conspire with the continuum ones to balance out to 0.
Well, if they have to balance, if for continuous members of the continuous spectra, it goes to minus infinity as you take beta to infinity. So it would have to have like infinitely many degenerate states or something like that. But yeah. Okay. Yeah.
I have a question about this constraint or the Z2 beta, Z beta connected.
Uh-huh.
Can I understand this as the same physics of the plateau and the spectral form factor?
Yeah, I think it's similar. Yeah. Yeah, I think I agree with that.
In this shed light on how we could understand the plateau?
I think it's similar physics, but in a different regime. So in the plateau case, like you're looking at, say, some part of the bulk of the spectrum and trying to analyze the discreteness of states there. Whereas here, it's the same thing, but at the edge of the spectrum. It's the same thing. It's just that instead of like Lorentzian time, you're going in Euclidean time, and so it's pushing you to the edge of the spectrum. Whereas in the spectral form factor, you're just like localized on some part of the bulk of the spectrum and looking at that at long times. That's the only difference, really. They're related by analytic continuation, I guess. Yes.
Is there so in the one eigenvalue instanton, there is some classical solution, right?
Yes, on the random matrix theory side, yeah.
Is there a similar solution in gravity?
Yeah, I think Sergio had some proposal for this thing, which was he was imagining that this is some sort of near extremal black hole with like a brain sitting there or something of that sort, where you think about the one eigenvalue instanton as like an extra brain. But I don't think this is clear yet. So we don't really know what the gravity description of that is.
This should be something within the rules of JT gravity.
Okay, so if you're, okay, so there's this regime of overlap. So if you're in this Airy limit where alpha is just order 1, then it really involves this resummation over all genus. So there's not really a classical solution within the rules of JT gravity. If you go to larger alpha, where this is a solution on the random matrix theory side, this goes beyond the regime of JT gravity. Like you really need some, like whatever is the completion of JT gravity. And so it's not so clear what that solution really means on the bulk side. Yeah, I think that's an interesting thing.
So if you go to super low temperatures, then you should like leave the Airy regime again, I think.
Yeah, so if you take alpha to be larger than this, that's like beta of order e to the S naught or something, that's outside this region.
Brains and JT dominates maybe?
Yeah, so these eigenvalue instanton, I think is roughly like that. Like this thing, when you take, say, beta of order e to the S naught, this separates by some order 1 amount. So it's very much like the ZZ brain. The random matrix analysis, yes, that still works. The Airy analysis stops working.
Somewhat less.
Yeah. I think that is basically what Sergio was trying to propose, which was this brain plus the black hole. Yeah, that's right.
Okay, if there are no other questions, let's thank Pratik Rath.